Hello, welcome students for the online lecture on fluid power systems. Today we are going to discuss the second module, that is pumps and actuators. Hydraulic pumps. So already we have discussed a basic hydraulic system consists of following major components: a reservoir, an oil supply tank, that is an oil supply tank. Next, pump and prime mover, that is the source of the power. Pressure relief valve, for system safety it is required. Control valves for direction and other controls. Cylinder or hydromotor, that is working element. Though each of the items is equally important for the system, the pump plays a specific and unique position in the system. It can be compared to the heart of a human being. The main purpose of the pump is to create the flow of oil through the system and thus assist transfer of power and motion. The pump is coupled to and driven by prime mover of the system, which is most often an electric motor. The inlet side of the pump is connected to the reservoir. The outlet or pressure side is connected to the control valve and thus to the rest of the system. Power is one of the most important parameter to carry out and useful work. No power, no work. Nature is so generous to provide free energy, and man has been able to convert one form of energy to another. Power as such is not contained except that of flowing water or wind. The oil used in the hydraulic system, which is generally an independent system or entity, is to be energized to the desired level with the help of many of the mechanical devices, generally pumps, available or designed so that energized or powered oil could be used for carrying out many useful and challenging work. This unit deals with various types of hydraulic pumps in detail along with the basic principle and theory of pumping. Details of the construction and working of pumps have also been provided for each of the pumps. Classification of pumps. Pumps are classified as positive displacement pump and non-positive displacement pumps. In positive displacement pump, again there are rotary type and reciprocating type, that is fixed or variable. In rotary type there are gear pump, vane pump, screw pump, and again in rotary also there are fixed displacement pumps and variable displacement pumps. Again it is divided into balanced pump and unbalanced pump. In reciprocating type there are axial piston pumps, inline type, bent axis type construction. Here also variable type is available. Radial piston, in radial piston stationary type is available, and rotating cylinder block is available. In non-positive displacement pump there are centrifugal pumps, axial flow pumps and radial flow pumps. Pump classification. Basically pumps can be classified as positive and non-positive pumps. Positive displacement pump. Positive displacement pumps are those whose volume changes from maximum to minimum during each pumping cycle. That is, pumping element expands from a small to a large volume. Here the volume goes on increasing and suction is going to take place. That is, the pumping element expands from a small to a large volume and is then contracted to a small volume again. Positive displacement pumps are used where pressure is the primary consideration. In these pumps, the high and low pressure areas are separated so that the fluid cannot leak back and return to the lower pressure source. The pumping action is caused by varying the physical size of the sealed pumping chamber. The pumping action is caused by varying the physical size of the sealed pumping chamber in which the fluid is moved. As fluid moves through the pumping chamber, volume increases and is finally reduced, causing it to be expelled. So when volume goes on increasing, the suction of the oil is going to take place, and when the volume goes on decreasing, the discharge is going to take place. In positive displacement pump, as the fluid moves through the pumping chamber, volume increases and is finally reduced, causing it to be expelled, alternately increase and then decrease the volume. Since the volume per cycle is fixed by the positive displacement characteristics of the pump chamber, the volume of the fluid pump for a given pump size is dependent only on the number of cycles made by the pump per unit time. A fluid moves through a pumping chamber, volume increases and is finally reduced, causing it to be expelled. Since the volume per cycle is fixed by the positive displacement characteristics of the pump chamber, the volume of the fluid pumped for a given pump size is dependent only on the number of cycles. In such pumps, the flow enters and leaves the unit at the same velocity. Practically no change in kinetic energy takes place. These pumps provide the pressure with which a column of the oil acts against the load and are hence classified as hydrostatic power generators. Advantages of positive displacement pumps. Positive displacement pumps are widely used in hydraulic system. They can generate high pressure. So positive displacement pumps generate very high pressure. In that too, if you use piston pumps, they will create more pressure than the vane pump gear pumps. They are relatively small and enjoy very high power to weight ratio. So output is very high. Input is less and output is more here. They are relatively small and enjoy very high power to weight ratio. The weight is less and power output is high. They have relatively high volumetric efficiency. They are relatively small and enjoy very high power to weight ratio. They have relatively high volumetric efficiency. There is relatively small change of efficiency throughout the pressure range. They have greater flexibility of performance under varying speeds and pressure requirements. Non-positive displacement pumps. Pumps where the fluid can be displaced and transferred using the inertia of the fluid in motion are called non-positive displacement pumps. Some examples of such pumps are centrifugal pumps, propeller pumps, etc. They are usually used for low pressure up to 40 bar and high volume systems. So in household and in irrigation purpose, we are going to use this non-positive displacement pumps where pressure required is less and discharge required is high. Because of their fewer number of moving parts, non-positive displacement pumps cost less and operate with less maintenance. The chamber in positive displacement pumps is connected so that as pressure increases, fluid within the pumping chamber circulates. The action of the mechanical drive in the pumping chamber speeds up the fluid so that its velocity accounts for its ability to move against the resistance of the system. For a given pump size, the volume of the fluid pumped is dependent on the speed of the rotating member and the resistance the pump must overcome. The impeller imparts kinetic energy of the fluid. Hence, centrifugal pumps are hydrodynamic or hydrokinetic power generators. So we'll see the construction and principle of positive displacement pump. As defined earlier, a positive displacement pump has to generate continuous flow of liquid and also has to supply the necessary force or pressure to the flow of the liquid. So it must create the pressure. There must be continuous flow of the fluid. Positive displacement pumps may be either reciprocating type or rotary type. These pumps can also be divided as fixed delivery, that is pumps with fixed displacement, constant delivery, in which the flow volume is constant and when the speed is constant. These pumps have no control of rate of flow. Variable displacement pumps. In variable displacement pump, the output volume, that is the flow rate of the pump, is variable. That is, in these pumps the flow rate is controlled to vary in a certain range at constant speed as per demand of the system. Reciprocating pump. Reciprocating pump are generally cylinders with a piston operating as a pump. They are available in various sizes, shapes, and driving mechanism. Due to high pressure, they are used for specified applications. Such pumps are capable of developing very high pressure. If the reciprocating principle is used in a rotary form, the pump using the principle is known as piston pump. Rotary pump. Rotary pumps are the most common in oil hydraulic systems when low to medium pressure is the prime consideration. When the pressure required is very high, at that time we are going for piston pumps. So otherwise we are going to use the rotary pumps. Rotary pumps are the most common in oil hydraulic systems when oil low to medium pressure is the prime consideration. Although there are many varieties of rotary pumps, out of those the three prime types are gear pump, vane pump, and screw pump. So in figure you can see the gear pump. So housing is there. Inside the housing there is a two gears are there. So low pressure side, it is connected to the reservoir through the pipes, and pressure side, pressure volume, that is the small volume side, it is connected to the system, and the oil is flowing towards the actuator. The pump which is pumped, the oil which is pumped by the pump, the oil which is discharged the pump, it is moving towards the actuator to do the work. To do the work, high pressure is required, and high pressure is created by this pump. So in gear pump, inside the housing there are two gears, and we can see the two shafts, and one shaft is connected to the electric motor. When you start the electric motor, the gears will start to rotate inside the housing with a very small clearance, in which is in terms of microns. So here, as the gears unmeshes, volume increases, and it will going to suck the oil inside it. And when the gear starts to mesh, so volume decreases, and it will start to discharge the oil. So you can see the pressure diagram. So at the inlet, pressure is low. As the oil approaches towards the outlet port, the pressure is high. Working of gear pump. As the gear unmesh, a partial vacuum is created at the inlet, drawing fluid into the chamber formed within the teeth. The chamber carries the fluid around the outside of the gears, where it is forced out as the teeth mesh against at the outlet, and any fluid left in the chamber is developed into high pressure. How pressure is created? A pump creates flow, and pressure is created by resistance to flow. That is, the pressure results whenever the flow of the fluid is restricted. As the fluid is drawn into pump chamber through the inlet port due to partial vacuum and reduces space, resisting flow in the upstream side causes pressure to build up. So you'll see the theoretical volume displacement of external gear pump. So you can see the gear with outer diameter DO and inside diameter DI, and W is the width of the gear tooth, VD is the volume displacement of the pump, N is the RPM of the drive gear, that is revolutions per minute, QTH means it is a theoretical flow rate or discharge, which is in meter cube per minute. So Q theoretical is equal to Vd into N. Vd will be the unit of the Vd is meter cube per minute and revolutions are revolutions per minute. Meter cube per Vd is in meter cube per revolution, and N is revolutions per minute. Revolution cancels, and you are going to get the Q theoretical, which is in meter cube per minute. So Q theoretical can be calculated by using the formula pi by 4 d naught whole square minus di whole square into width of the gear teeth into RPM of the motor. So Q theoretical will be in meter cube per minute. So volumetric efficiency is given by Q actual divided by Q theoretical into 100. Q actual will be less than Q theoretical due to internal leakages. So if you observe the graph, you can see the leakages. Due to leakages, Q actual is less due to the leakages. Q theoretical will be less than Q actual will be less than Q theoretical due to the internal leakage, and internal leakage increases with pressure. Actual discharge pressure characteristic for a gear pump speed for a given pump speed. Pump slippage. So what is pump slippage? Pump slippage is the difference between the theoretical discharge and actual discharge denoted by S. S is equal to Q theoretical minus Q actual. So S is equal to Q theoretical minus Q actual divided by Q theoretical into 100. So that will give the pump slippage. So difference between reciprocating and rotary pumps. If you compare the reciprocating pump and rotary pump, reciprocating pumps are complicated, rotary pumps are simple in construction. Reciprocating pumps have high power to weight ratio. Reciprocating pumps have high power to weight ratio. Rotary pumps have low power to weight ratio. So in reciprocating pumps you are going to get high power, and rotary pumps you are going to get the low power. Reciprocating pumps, there is a direct coupling can be done. Coupling to a prime mover, it is direct, and in coupling to the prime mover in rotary pumps it is indirect. Discharge of the reciprocating pumps is pulsating or discontinuous, and discharge of the rotary pumps is continuous and pulsation. So we have shown the graphical symbols for the reciprocating pumps and rotary pumps. So we will solve on the problem. A gear pump has gears of external and internal diameters of 75 mm. So D naught is given 75 mm. So outside diameter of the gear, and 50 mm is the inside diameter of the gear. And volumetric efficiency is 90% at rated pressure. What is the actual flow rate of the pump if the speed of the pump is 1000 rpm? So outside diameter of the gear is given, D naught is equal to 75 mm. So inside diameter of gear, di is equal to 50 mm, that is 50 into 10 to minus 3 meters. Width of the gear is W, that is 25 mm. So 25 into 10 to minus 3 meters. So volumetric efficiency is given 90%, that will become 0.9. So if we want to calculate the actual discharge, and the speed of the pump is given 1000 rpm. So we know that volumetric efficiency is Q actual divided by Q theoretical, and Q theoretical is given by pi by 4 in bracket d naught whole square minus d naught di whole square into width of the gear teeth into N. So pi by 4 into 75 square minus 50 square into 10 to minus 3 whole square, 10 to minus 3 whole square means we have converted the mm into meters. So into 25 into 10 to minus 3 means it is 25 mm width, which is converted into meters, and 1000 is the rpm of the motor. So Q theoretical will come 0.061 meter cube per minute. So this is the theoretical discharge of the pump, which is given in meter cube per minute. So we are going to get this one Vd into N, and Vd is nothing but it is pi by 4 d naught whole square minus di whole square. That is volumetric displacement of pump per revolution. Vd into N, if you multiply Vd into N, you are going to get Q theoretical. So theoretical discharge is 0.061 meter cube per minute. So if you multiply by 0.9 to that theoretical discharge, you are going to get the actual discharge, which is equal to, so 0.9 into 0.061, that will become 0.05522 meter cube per minute. So if you see the result, so just now we have discussed that always the actual discharge is less than the theoretical discharge due to the losses. 0.05522 is the actual discharge, and theoretical discharge was 0.061 meter cube per minute. So if you convert that meter cube per minute in liters per minute, you must multiply by 1000, because 1 meter cube is equal to 1000 liters. So you are going to get the answer 55.22 liters per minute. That is the actual discharge of the pump. 55.22 liters per minute. So pi by 4, 75 is the outside diameter and 50 is the inside diameter. So 10 raised to minus 3 means we are going to convert into meters. Into 25 is the width, and 1000 is the RPM of the motor. So we are going to get the theoretical discharge 0.061 meter cube per minute, and if you multiply 0.9, that is the volumetric efficiency, to the theoretical discharge, you are going to get the actual discharge, which is equal to 0.05522 meter cube per minute. So if you convert in liters per minute, you must multiply by 1000, because 1 meter cube is 1000 liters. So you are going to get actual discharge of pump is 55.22 liters per minute at 1000 rpm. If the rpm increases, again the discharge is going to increase here. So next problem, determine the volumetric efficiency of a gear pump. We want to find the volumetric efficiency, that is nothing but Q actual divided by Q theoretical. Determine the volumetric efficiency of gear pump of external diameter and internal diameter of 75 mm and 50 mm diameter respectively, and width of the gear is 50 mm if the actual discharge is 30 liters per minute at 1800 rpm. So what are given things are, d naught is equal to 75 mm, di is equal to inside diameter, di is given 50 mm, width of the gear is given 50 mm. Therefore Q actual is equal to 30, it is given Q actual is 30 liters per minute. If we convert into this meter cube per minute, it will become 0.03 meter cube per minute. So 30 divided by 1000, it will come in meter cube per minute. So if it is in meter cube per minute, if you multiply by 1000, we are going to get the liters per minute, but here 30 liters per minute is given, therefore divided by 1000, you are going to get the answer in meter cube per minute. That is Q actual is 0.03 meter cube per minute. So actual is given. So you want to find the volumetric efficiency, Q actual divided by Q theoretical. So we know the formula to find the Q theoretical, that is Vd into N. Vd means it is volumetric displacement, that is pi by 4 d naught whole square minus di whole square into W. So if you multiply by N, you are going to get theoretical discharge. So pi by 4, 75 minus 50, 75 whole square minus 50 whole square into 50 into 10 raised to minus 3 whole square into 1800. So that will come Q theoretical, that is equal to 0.110446. So volumetric efficiency is nothing but it is the Q actual divided by Q theoretical. Q actual is given, and we are going to we have calculated Q theoretical. If you multiply by 100, you are going to get the percentage. So volumetric efficiency is 54.32%. So remaining things we will discuss in the next class.